Chapter 13 here about equilibrium. So last time we talked about pretty much all day ice tables and how to solve ice tables, and we saw really several different sort of ways that you will be asked to sort of solve ice tables in this particular class. One using, obviously, we had a situation where we had like a perfect square. We had a situation where we did have to use quadratic to solve it. And then we also saw a situation where you can assume that x is equal to 0. Remember that you can assume that x is equal to 0 only in a case where your k value is small. And the purpose of that is, again, when we do our ice table, if our k value is really small, that means that not a lot of reactants will be going over to the product side. And that means when we do look at the sort of x value here, it would be a relatively small number. And we can make the assumption that x is equal to 0. Remember, we can't get rid of all the x's. It's really just the x's that you would be subtracting from a number or adding to a number. Obviously, for example, if we started with 0 of our products and we ended with x there at equilibrium, since we started with 0, whatever we would make, even if it's a small amount, would be relatively a lot compared to where we started with. Also remember that we do use the 5% rule here to check if our assumption is good or not. Again, to do the 5% rule to check it, you basically take the x value that you got, you divide it by basically the number you were going to subtract or add x to, and you times it by 100%. So basically the initial concentration is really what that is on the bottom there. And you take x divided by that. If it's 5% or less, you're good. You can keep that x value and basically solve for what you're looking for. If it is over 5%, then you pretty much got to roll back. In most cases, go through the quadratic formula there to solve for x when you do it. Any questions on ice tables and how to do them? Okay. So the last thing we're going to talk about here is Le Chatelier's principle. And Le Chatelier's principle is really when we have a system that is sort of at equilibrium. So we have the system, it reaches chemical equilibrium. And then what we do to the system that is at equilibrium is we add some type of stress to it. So when we add some type of stress to the system that's at equilibrium, which, as we've talked about a number of times, basically means that the rate of the forward direction will equal the rate of the reverse direction. That is basically going to, for lack of a better word there, screw up the equilibrium. So we're going to add a stress to it. It's going to really mess up the equilibrium. And when it messes up the equilibrium, what's going to happen is the reaction itself is going to want to sort of correct itself to get back to the equilibrium position. So there's going to be some type of correction for that reaction to sort of return to an equilibrium state of the forward reaction and the reverse reaction equaling each other. And the type of correction basically will be either it will sometimes be referred to as shifting to the right, which basically means we need to make some more products to get back to equilibrium. It will sometimes shift to the left, which obviously would mean we need to make some more reactants to get back to equilibrium. Or we may even have a situation that could occur that, even though we sort of added a stress to the system, there actually will be no change that will occur. So even though we did something to it, overall it will cause really no effect in equilibrium. So what are these sort of stresses that we're talking about? Well, there's several different types of stresses we're going to talk about. One is involving concentration. So in terms of concentration, you could either add more or remove concentration. Volume and pressure. So if we're dealing with sort of a gas situation here, the volume and the pressure are stresses you can play with. Temperature is another one that you can play with. And adding a catalyst is another situation. So these are sort of the stresses that you could put on a system that's at equilibrium. It again will sort of adjust to fix itself to get back to equilibrium. Will it end up with the same amount of guys on both sides? It will not from where it started, but again, it will return to that equilibrium position, which means it will have the same equilibrium constant as long as you didn't change temperature. So obviously a reminder again, temperature is the only thing that will actually change the value of the equilibrium constant. Everything else will basically remain the same. So let's talk about each of these here and sort of how it affects it. We're going to start with concentration. So concentration, basically, as I said, there's really two things that you could do. You could either add more or you could remove. So those are pretty much your two options there in terms of concentration. When we add more to a system that's at equilibrium, what will happen is the equilibrium will shift away from the side you added it to. When we remove concentration, it will actually shift towards the side you removed. So when we talk about towards the side you removed or towards the side away from it, what we're talking about is if you added more reactants, you would then make more products. It would shift towards the product side. If you added more products, it would go away from the product side and go towards the reactant side, and vice versa, obviously, with the removing part. Adding is a pretty simple concept. You basically could just go to the shelf, grab a reagent, right, that is in your equation, and you could just dump it into your beaker and you will basically be adding more of whatever that is. Removing, if I want to remove something from a solution, do I just reach in and grab it? Probably not a good idea. How can we remove things from solution? Say again? Not necessarily diluting, but we can add something to it, for example, that makes a precipitate, right? Precipitate is a solid. Solids are not included in the equilibrium constant. So that's essentially like reaching in and grabbing some type of ion out of the solution, right? It's now going to be locked into that solid. And that would be essentially one way that you can remove something. That is a way that you could actually see it happen. You'll actually see the solid being formed. Another way that you can remove something from solution, and you may not be able to sort of physically see it as you do it, is actually the formation of water. So if you have some type of solution that has hydroxide, OH minus floating around, or a solution that has H plus floating around in it, if you add either an acid or a base to a solution like that, you will form water. Water is a pure liquid, right? And that would be like removing OH minus or removing H plus from the solution. So those are two very common ways that we could actually reach in and remove things from the solution. So let's talk about really what we're seeing here. So let's just say we had sea salt or something like that. So we'll say this guy over here on the left is the reactant side. This guy over here on the right is the product side. So if I decided I'm going to add some more products and put an extra guy on there, what's going to happen is that equilibrium will now be kind of messed up because we got a couple guys on this side. This guy is going for a ride up this way. Not so happy. It's advanced stick figures. They have faces. Intro to stick figures, no faces. So in this case, right, to fix the situation, we need to put more people on the right or more people on the left. Yeah, so we added to the right, so it's going to shift away from the side we added. we're going to put more people back on over there, and we will once again sort of get back to a equilibrium position here in this case. So when we add, it goes away. So AA is a good way to remember that, add away. And we can see kind of the same effect here, obviously, if we did our initial here. And this guy decides he's going to basically hop off of it. And when he would hop off, we would end up with this situation here. Again, unhappy on that side. And in this case, to fix it, we're going to actually need to put another person kind of back on the other side. So we're actually going to shift towards the side that we removed it. It will once again get back to our equilibrium position here. And that's it. Any questions on that there? Take home messages, don't be on that side, apparently. Bad idea to be on that side. Okay. So, if we had something like, A plus 2B goes to 3C. And in this case, if I added more A, which way should it go? Yeah, so we added A, which is a reactant. So it's going to cause the equilibrium to shift away from it and making the product side. Why is it doing that? It's doing that because we now have a lot more A available to react with B. And what that's going to do is basically kick off the forward direction, right? And that is why it's going to basically start making some products in that particular case. If we remove some C, which way should it go? Yeah, so it should also, in this case, go to the right. So kind of the same idea. And when we remove C, now the product side is really deficient, which means what we mainly have still in solution now is the reactants, which once again will kick off the forward direction in this particular example. Any questions on that there? Okay, another sort of important relationship is volume and pressure. And I usually think of these two guys sort of together. And when we think about pressure, right, we think about really gases. So this involves really sort of equilibrium that involves gases. And we remember our good friend like Boyle, for example, right? There was a relationship between pressure and volume. As the pressure goes up, what happens to the volume? Volume goes down, opposite relationship, right? Inversely related. Smaller volume, less room for the gas molecules to fly around. That means we're going to see an increase in collisions, an increase in pressure. And vice versa, obviously, if the pressure starts to drop, we would see that the volume actually is increasing. Again, larger volume, more room for everybody to fly around in, a lot longer for collisions to occur, and the pressure obviously starts to drop down. So if we think about this, what happens in this situation is if the pressure goes up, that's sort of the change that's occurring as a result of the stress. So what we really want to do is kind of bring the pressure back down to sort of fix it. And because the volume's related to it, if I have a very small volume, do I need more or less gas molecules to bring the pressure back down? So if I put more gas molecules in a really small area, would I expect the pressure to go up or down? It would actually go up, right? So if you had a lot of gas molecules in a very small area, they definitely will be running into everybody, right? And a lot more collisions, and we would expect the pressure to go up. If you had a much larger volume, right? Or actually, that's not right. If we had the same volume here, but a lot less gas molecules flying around, right? There's going to be less collisions in that case, and that's going to bring the pressure down. So what we would want to do is it would actually shift to the side with the least number of gas molecules. And again, that could be left side, right side. You have to look at the equation. You have to look at everybody that's got a G in the equation, right? Count up the coefficients. and decide how many gas molecules are on each side. Opposite is true here in our pressure situation. If the pressure is lowered, the volume is raised. And as the pressure comes down, which is sort of the change, what we want to do basically is bring the pressure back up. So in that larger volume, we would need a lot more gas molecules in there to increase the collisions. So in this case, it would shift to the side with the most gas molecules. And again, that's obviously dependent on the equation that you're looking at as to, how many gas molecules you have on each side. The way I personally sort of remember it is by volume. Small volume, I need less people in there. Larger volume, I need to fill it by putting more gas molecules in there. So a good way to sort of remember it is by volume. And again, small, less, and larger volume, we need more gas molecules to fill it. So if we looked at an example here of do R2A plus R3B, and we'll do R4B. So I should learn the alphabet. I think C comes after B there. C, there we go. All right, so if we have, say, this guy here, let's try that again. All right, 4C. Okay, so let's try this. Let's say we, in this case, added some C. Let's say we removed some B. Let's say we increased the volume. Let's say we increase the pressure, and let's say we added some A. All right, so for each of these cases, will it shift to the right? Will it shift to the left? Or will there be no change? Let's take a minute or so and see what you come up with. Okay, let's take a look. So here we're going to add C, and C is a product. So when we add it, we'll shift away. So we would expect it to go to the left in this case. Again, the idea here is we've now increased our product side. That's going to kick off the reverse reaction happening a lot more to sort of fix the unbalancedness. In this case, we are removing B, which is a reactant. So again, when we remove something, it will go towards the side we're removing it from, which means, again, in this case, it will also go to the left. Any question on those first two there? Again, for the same reason, we're sort of depleting out the reactant side, which means we have a lot more products. So that is going to, again, kind of kick off that reverse reaction happening. In this case, we're going to increase the volume, which the effect on that is really that the pressure is going to, in this case, then drop. And really, we could think about it in terms of volume. In a larger volume, we need to kind of counteract the pressure coming down. So to do that, we need a lot more gas molecules to kind of bring the pressure back up. So in this case, is going to shift to the side with the most gas molecules. Again, very simply found by looking at everybody that has a G and basically adding the coefficient. So on the left-hand side, there's basically 5 gas molecules. On the right-hand side, there's actually only 4 gas molecules. That means in this case, it will also shift there to the left. Any questions on that one? Higher pressure means really lower volume. And again, the smaller volume, which is why the pressure starts to rise, to fix that, to bring it back down. As we talked about before, we actually need to go to the side with the least number of gas molecules. So doing our accounting there before means we will actually shift to the right in this case. And lastly here, adding A, which is a reactant, causing a lot more reactants to be present, kicking off really the forward direction of this reaction. And we should expect it to head to the right. Any question on concentration, volumes, pressures? Okay, so those are 2 very common stresses that you could do to a system at equilibrium that will sort of mess it up. The next really big thing that you could do sort of to a system that's at equilibrium is change the temperature. So temperature is the next biggest thing that you could do. And the good news about temperature is it works the same way as concentration. So changing the temperature basically works the same way as concentration. What that means is if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. So the idea here is we think of temperature as either a reactant or product. So what helps us determine whether or not a sort of temperature or energy or heat is a reactant or product? It has to do with the type of reaction you have. And what I mean by that is it exothermic or endothermic? So let's remind ourselves about a couple of these things. First off, for our exothermic reactions, if it is exothermic, typically the delta H value is positive or negative. It is negative, yes. So it is typically negative if it's exothermic. It is being released, right? Heat and energy is being released, which is what that basically means. And what that means is because it is being released, when we look at a reaction that is exothermic, we think of energy or heat as being a product. So that means if the reaction is exothermic and we increase the temperature, that would be like adding more products, which means it should shift to the left-hand side away from that. And if we decide to put everything on ice in an exothermic reaction, which would be lowering the temperature, it would be like removing a product and it would shift towards that side. Endothermic obviously is sort of the opposite here. Endothermic means that we're going to absorb energy. Delta H values for things that are endothermic are positive, and that means that it's being absorbed. And what that means is when we think about endothermic, heat and energy is considered a reactant in this case. So it's sort of the opposite of what we just talked about. If you have an endothermic reaction and you increase the temperature of it, it would be like putting more heat and energy into the reactant side, which it would shift away from the reactant side to the product side, and vice versa. If you removed heat and energy or temperature or lowered the temperature, that would be like you're removing reactants and it would come towards the reactant side in that particular case. So in terms of temperature, it's really important to figure out whether or not the reaction is endothermic or exothermic. I would say probably 90% of the time, book type problems will just simply give you the delta H value at the end of the reaction. And again, it doesn't really matter what the number is, but it's actually the sign here that's important. Again, if it's a negative sign, it will tell you it's exothermic. If it's a positive sign, it will tell you it is endothermic. Any questions on that? And again, this is the one area though that, as we talked about, that actually does affect the value of K, is affected by temperature. And what we talked about is, again, if you compared the K value at 25 degrees Celsius to the K value at, say, 50 degrees Celsius, the comparison between 25 degrees Celsius and 50 degrees Celsius will yield you a different K value. But again, if you kept it constant at 25 degrees all the way through, the K value would stay the same. If you kept it constant at 50 degrees all the way through, the K value would be the same. But comparing the K value at those two different temperatures, you will get some different values for it. Any questions on sort of temperature here? The last thing that, again, sometimes is included with Le Chatelier's principle is adding a catalyst. And as we talked about, in terms of Le Chatelier's principle, it really will have no change. You'll just kind of get there quicker. But remember, a catalyst is typically something that will speed up a chemical reaction. And remember that it essentially does that by lowering the activation energy, right? So if you have a sort of an uncatalyzed versus a catalyzed reaction, it lowers that activation energy, which makes obviously the reaction occur a lot faster. In terms of, like I said, sort of Le Chatelier's principle really have no effect on it. Other things that will sometimes be asked and doesn't really have an effect is a lot of times if you add something that's like a noble gas, for example, that also will typically get you to a no change that will occur, again, because noble gases are chemically inert, which means they don't really react with anybody else other than themselves. So that is also something that you could add to a system that really would not have any type of effect. Any questions on any of those there? All right, so let's just take a look here, and then make up one here. We'll do like A plus B goes to 6C. We'll do delta H is positive 125 kilojoules. All right, so let's say we decreased the pressure, we added some B, we lowered the temperature, we increased the volume, we added C, we removed A, we added a catalyst, and let's say we then, well, we're at that's good, I think. All right, left, right, or no change in these cases. It means the volume went up. And to fix that, we again need more gas molecules in that larger volume. So looking at our equation here on the left-hand side, I got 3 and 1, which is 4 gas molecules. Again, just simply counting the coefficients there for anything with the G. On the right-hand side, we obviously have 6 gas molecules. So in this case, it would shift to the right-hand side, which is our 6 gas molecules. Adding B, so B is a reactant, so when we add, it will go away, so it should go from the reactant side to the product side and also shift to the right. Any questions on those two? We're going to be decreasing the temperature, so we want to determine what type of reaction we're dealing with. So they did give us a delta H value, and really the only thing that's important is right there. It is a positive number, which means it's an endothermic reaction. That means that heat would be considered a reactant. And in this case, if we lowered the temperature, that would be like removing heat and energy from the reactant side, which should cause it to shift towards that side, and it would go to the left there. Any questions on that one there? We increased the volume. So again, that is basically the exact same thing as what we had when we lowered the pressure. So increasing the volume again means we should go to the side with more gas molecules, which means we would end up there to the right. We're adding C. C is a product, so we're going to add away, going to cause the reverse reaction to happen, and it would shift to the left. We removed some A. So A, in this case, a reactant. Removing the reactant will cause it to go towards the reactant side, as we really have more products than reactants. So that reverse reaction is going to basically happen. And then adding our catalyst here should be a no change situation. Any questions on any of those? So really when we think about, sort of what's happening here, if we did something to it that sort of increased sort of the concentration on one side or the other, It's really just going to cause that reaction to occur. If we did something that sort of depleted one side or the other, it's going to cause the other reaction to occur towards it to sort of fix it. You know, kind of like you take something away, it's kind of like a hole. We got to throw some dirt in the hole, right, to fix it, and it's going to go towards that side. Any questions on that there? Okay, so I think this is yeah. There is, and that would be a no change situation. So that's another way that you could end up with sort of a no change in that case. Yep. So this is sort of what we talked about here again. Shifts away from the added component or concentration, goes towards it, and obviously K will change depending on the temperature. And we want to think about it as being a reactant or a product, depending on endothermic or exothermic. And our pressure here, an inert gas will not affect equilibrium, but decreasing the volume will shift it towards the side with fewer moles. So let's take a look at this guy here, and let's just say that the delta H on this guy was negative 133 kilojoules. Just made up that number, clearly not right. All right, so in this case, we're going to increase the temperature. We're going to add some H2. We're going to increase the pressure. We're going to remove some N2. We're going to, let's say, decrease the temperature. And sounds good. See what you end up with. So in this case, we'll start with increasing the temperature. So here we look at our delta H, and it is negative, which tells us it's exothermic. Also tells us that we consider kind of heat and energy to be a product. So in the first case here, we're going to increase it, which would be like adding more products, which means it should shift away from that side and should go to the left. In this case, we're adding H2, which is a reactant. So that should cause the forward direction basically to occur and shift it that way. We're increasing the pressure, which means that our volume is really getting smaller. So in the smaller one, we want less gas molecules. Looking here, we got 4 on this side, gas molecules, and we got 2 on that side. So we would want to shift it to the right in this case. Removing N2 will cause it to shift towards that side, and decreasing the temperature obviously will have the opposite effect of increasing. And again, since it's exothermic, that would be like removing products, which would cause it to shift towards the product side, and it should go that way. Questions on Le Chatelier's principle, how to figure it out there? Okay. Just want to look at one more here. It's just sort of our question. So, and again, I don't know if the 2's there on your notes or not, but as was the earlier question a second ago, you know, if we did have a situation such as this guy here, and we did something like, you know, increase the pressure. Again, in this case, if we increase the pressure, the volume would go down, and we would want to shift to the side that has the least number of gas molecules. But looking at this, we do have 2 gas molecules here, and we also have 2 gas molecules here, which basically means it's a push. There is no side that's more or less, and this would be, again, another situation where you would end up with a no change in this particular case. So yeah, that absolutely can occur in that situation. All right, any questions on any of that stuff there? All right, so that should wrap up this chapter. That also means that our exam's next week, I believe, right? I can go with Tuesday probably because Thursday's a holiday, I think. So I'm not sure what holiday that is at this point, but I see on the schedule it says holiday, so we'll go with it. So it is on the first 2 chapters. So that's kinetics, and that is obviously equilibrium. Everything is fair game. Again, you won't be provided any formulas, but any type of constants or any of those type of conversions would be provided to you. And that also should mean that the homework for those 2 chapters will be due on that day as well. So there'll be a box again for you to upload that to Canvas. Any questions on any of that there? Okay, then we're going to roll into chapter 14, which is a ginormous chapter of everything bad happening in it. So we'll get started on it. Just give me a second here to get it up and going here. Yeah, so just to be the first two chapters. So for us, you guys started with kinetics, so that's kinetics, which should be the first chapter, 12, I believe. And then 13, which we just finished here, should be the equilibrium chapter. All right, I'll do that there. All right, so obviously what we are looking at here in just a second is not on this exam. So this would be obviously exam 2 material here. Go. Okay, so like I said before, chapter 14 is a big chapter. Yeah. And in most books, it's like 2 separate chapters, but your book, they just kept throwing it into chapter 14. So part of the chapter, not terribly bad, but towards the middle of the chapter and stuff like that, we will be getting into the part of the class that is very difficult for a lot of people, which is titrations and buffers and those type of things. So this is sort of the big part of the class coming up through this chapter and the next chapter. A lot of really where you got to understand the conceptual aspect of what's going on to be able to do the math correctly. So it's a lot what's going on here. Some of this might be some review for you guys as well, although they don't cover it in Chem 50, but in Chem 40, they used to cover things like acid and bases and pH, I think. So we're going to open up with just acid and bases and pHs, get into some calculations of weak acids and weak bases. And then, like I said, towards the end of this chapter, middle or end of this chapter, we get into really some of the heavy stuff, the buffers and the titrations and stuff like that. So this chapter will go on for a while here as we go through it. All right, so let's start with acid and bases and some of the ideas of acids and bases. Acids have a sour taste, something like vinegar, which is acetic acid, citric acid. They react with certain metals to produce hydrogen gases, as you may be familiar with. That is like a single replacement type reaction, right? So if you had something like zinc plus some hydrochloric acid, the zinc would come in obviously and kick out the hydrogen in that case. The result of that is you would produce hydrogen gas, so you would see bubbles and all that good stuff, and some zinc chloride, right? They also react with carbonates or bicarbonates to produce carbon dioxide and water. And an example of that would be if you took something like hydrochloric acid and a little sodium carbonate, you'll get like a double displacement reaction where you'll form carbonic acid plus some sodium chloride. Probably do a little balancing there. Maybe that. And in this case, as you may be familiar with, carbonic acid actually will not hang around a very long time. It'll go through a decomposition reaction and very quickly form water and some CO2, plop, plop, fizz, fizz, a little Alka-Seltzer type deal in that case. Bases, on the other hand, they feel very slippery. A lot of bases are soaps, or a lot of soaps are bases, I guess is the way to put that. Drain cleaners and stuff like that. In terms of acids, just to make sure, right, we're all on the same page, so we don't say like, hey, that acid, whatever that thing is, right? Real quick reminder of the nomenclature, right? 2 acids. Really, when you're naming acids, it involves whether or not there is oxygen is really the big thing. If it has oxygen, so is sometimes referred to as an oxyacid, hence it has oxygen. If the answer is like, no, there is no oxygen, then the acid is hydro something ic acid, like HCl has no oxygen. So hydro, the middle part is the negative guy, chloric acid. HBr, which is hydrobromic acid. And typically acids do have the AQ symbol next to it, which is aqueous, because basically the definition of an acid is the ability basically to produce H plus as it floats around in the solution. If the acid does have oxygen, it will usually contain a polyatomic ion, which, as you might be familiar with, ends in either ate usually or ite, those polyatomic ions. So if the answer is yes, and your polyatomic ion ends in ate, it is something ic acid, like HNO3. NO3 is NO3 minus, which is nitrate. This becomes nitric acid, right? H2SO4. SO4 is sulfate. That is sulfuric acid. If your answer is yes and your polyatomic ion ends in ite, then it is something OUS acid, like HNO2. NO2 is nitrite. That becomes nitrous acid. Yeah. So as a reminder, again, hydro is only for acids that do not contain oxygen. And there is no hydro in anybody else other than those guys. And again, the other guys that do contain oxygen, either ate or ite, gives you ic or us. Any questions on that quick review of nomenclature of acids? Okay, so now you could call things correctly, hopefully, rather than, that thingy there that's like an acid type thing. All right, so sort of an early definition of acid and bases came from the guy like we just talked about when we did the Arrhenius plot. He did a lot of work with electrolytes, and if you remember, electrolytes are things that break apart in solution. They produce ions, they conduct electricity really well. And basically, he basically said that an acid is really a substance that's able to produce H plus or H3O plus ions in solution. And for all intents purposes in acid-base chemistry, H plus and H3O plus, which is actually the hydronium ion, that is a polyatomic ion, they're basically the same. Now, you will see them used interchangeable in formulas. You'll see it used interchangeable in actual equations. I personally use H plus most of the time, but pretty much anywhere I put H plus, you could put H3O plus. It works basically the same thing. The real difference is really what we see there up on top is whether or not you include water with your acid in the reaction. If you include water, you produce H3O plus. This is really just showing hydrochloric acid going for a swim and breaking apart. You could kind of simplify that reaction above by just simply writing HCl breaks apart into H plus and Cl minus. So they are both equivalent reactions. They mean basically the same thing. The only difference is a lot of times people with acids will not include the water as part of the reaction there as a reactant, and you don't get the H3O plus, but they basically are represented the same way. He basically said that a base was a substance that can produce hydroxide or OH minus in solution. And in terms of bases, a lot of strong bases, for example, come from group 1 and group 2 on the periodic table. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. Those guys that have actually OH in it are typically strong bases. That is also why group 1 is called the alkali metals, right? Group 2 are called the alkaline earth metals. The word alkaline means basic. So that's where a lot of bases come from and why those guys are sort of named that way. A very good thing to keep in mind as we go through this chapter and do calculations with acid and bases is sometimes you need to make a decision of, is it going to be an acid? Is it going to be a base? Or should I use like a acid value to do the calculation or a base value to do the calculation? Writing the equations correctly will help you decide that, because pretty much if you see on the product side some H plus or H3O plus, you're probably dealing with some type of acid situation and should be using sort of acid values. If you look on the right-hand side and you see hydroxide there, it is probably some type of basic situation. So that's a very simple way that you can make some educated decisions later on as we talk about it. So don't forget that sort of very simple idea. The next really major sort of definition of acid and bases that really dealt with bases that maybe did not have hydroxide in it is the Bronsted-Lowry. I don't know why on this slide he always gets left off, but it is the Bronsted-Lowry definition. And the Bronsted-Lowry definition of an acid is a proton donor, and a Bronsted-Lowry definition of a base is a proton acceptor. When we're talking about a proton, that is another name for H+. H+ is sometimes called a proton because hydrogen has how many protons? 1. How many electrons? 1. How many neutrons? 0. So because it doesn't have any neutrons, the only way it becomes positive is to lose its electron, which leaves it just a proton. So that is why it's called H+. So it's really important that when we're talking about sort of the Bronsted-Lowry definition of a acid or base, we're talking about a proton being donated or accepted, but it's not just the hydrogen. The plus is important because it actually does change the overall charge, right? If somebody gains the H+, it becomes 1 more positive. Somebody loses the H+, it becomes 1 more negative. So it does affect the overall charge. So in this sort of definition here, what's going to be happening is it's actually the ammonia here, the NH3, that's going to accept the H+ coming over from water. That means in this case, it is actually the water that's acting as the acid. It is the one donating the H+. The NH3 is acting as the base that is accepting the H+. And sort of a consequence of the Bronsted-Lowry definition is we actually get some guys on the other side of the arrow that are actually related to the guys on the left-hand side. Our base on the left-hand side is related to what is known as the conjugate acid on the right-hand side of the arrow, while the acid on the left-hand side of the arrow is related to what is known as the conjugate base on the other side of the arrow. The important relationship between those two things are the only difference that happened in this case is water donated only 1 H+. So the relationship between the base and its conjugate acid is it will have 1 more H+ as it goes across the arrow. And the relationship between the acid and its conjugate base is it will have 1 less H+ as it goes across the arrow. So that's a really important definition. Your acid and conjugate base, the absolutely only difference that there should be is 1 H+, and your base and your conjugate acid also should only be a difference of 1 H+. If it's any more different than that, they are not related to each other in this relationship here of an acid and its conjugate base. The last thing here is the regular old run-of-the-mill acid and bases are found on the left-hand side of the arrow, the reactant side of the arrow, and your conjugate acid and bases are found usually on the right-hand side of the arrow. Any questions on that there? All right, so take a second here and decide, are any of these acid conjugate base pairs or conjugate acid base pairs? All right, so let's take a look. So really the question is, if you're not sure, what you should be looking at is the difference really only 1 H+? And that's really the only difference that there can be between them. So looking at the first one here, it is a difference between H+, 1 H+, but there's also a difference of an oxygen there. One has the oxygen, one doesn't. That means that this guy would not be a pair. H2SO4 and SO4 2- would also not be a correct pair because the difference here is not 1 H plus, but it actually is 2 H plus difference. So that is too much. NH4 plus and NH3, those guys are related to each other and they are a pair. Again, if you put the H plus onto this guy, you would end up with NH4 and a plus, which is the other guy. So this guy is a pair. Or you can take the H plus off the other one. H3O plus and OH minus, again, are too far away from each other. They are a couple of hydrogens away or H pluses away, and clearly it cannot be that one. So it looks like the only pair here is our NH4 plus and NH3. Any questions on that one there? Now, something you might be wondering why these guys are not pairs, other than the fact that there is more than 2 H pluses. And the reason is, this is what's referred to as a diprotic acid, something like sulfuric acid. Diprotic acid means it's got 2 hydrogens to give, basically. And although we oftentimes learn, like in Chem 550, whatever that number is before this class, Chem 50, that's 253. I was getting close to it. So in Chem 50, we think about it as like losing 2, and we think that they actually do both just pop off all at once, and they actually don't. So hydrogens, when they come off of acids, actually do come off one at a time. So what would happen with something like sulfuric acid is actually the first thing that would happen is it would drop that first hydrogen and actually form HSO4 minus. And then what would happen is the second process would be that HSO4 minus would then drop off the second hydrogen and make SO4 2 minus. And it's sort of a step-by-step process that this occurs. When you think about it from maybe Chem 50, what you actually see most of the time is actually the overall reaction of adding these guys together. This guy and this guy cancel, and that leaves you H2SO4 goes to 2 H pluses and sulfate. So a lot of times earlier on, if you ever looked at this stuff, you would look at it more as the overall reaction. But as the hydrogens are coming off, it's actually a 2-step process that's occurring here. And that is why H2SO4 and HSO4 minus, these guys are pairs, and the HSO4 and the SO4 2 minus, those guys are pairs, but going directly from H2SO4 to SO4 2 minus, they are not pairs, again, because it's more than one H plus difference. Any questions on that there? So why don't you try this one? We have aniline, which was isolated. What would be the formula of the conjugate acid in this case? Think about what we were just talking about. And really what we're just talking about is we have an acid plus a base. And on the other side, we have a conjugate acid and a conjugate base. All right. And again, the acid goes with the conjugate base, and the base here goes with the conjugate acid. So sometimes they may not be nice enough and tell you what you're dealing with. So you want to kind of think about, what am I looking at? So let's just say they weren't nice enough to tell us that this is a base, but they do want to find the conjugate acid, right? So if we wanted to find the conjugate acid, we would go, okay, I'm looking for the conjugate acid, which means if I think about it backwards here, what I am looking at is a base. And if you know the definition of a base, which is something that should accept an H plus, that's what you would want to do in this case. And that means that because what I am looking at here would be a base, the conjugate acid would actually accept the H plus. And basically all we need to do is add an extra H, I'll just put it at the end, and the plus. And that should be our conjugate acid in this case. So sometimes it's important to think about, sort of what you're looking at, and just, in this type of question, it is pretty much an H plus. The key is, do I put it on or do I take it off? So if you just kind of think about it backwards and you know what you're dealing with and you know the basic definition of a Bronsted Lowry acid or base, that's all you need to do is either put it on or put it off, which looks like in this case, maybe number 2 looks like the right one, I think. Question on that one there. All right, so why don't you try HCO3 minus. Let's do the conjugate acid. And let's also do what is the conjugate base. So in one case, I want what the conjugate acid would be. In one case, what would be the conjugate base. Starting with HCO3 minus a little bicarbonate. Okay, so again, in these type of problems, that is really your decision, which is, do I put it on or do I take off the H plus in this situation? So we'll start here with the conjugate base. So again, in this case, if I am looking for the conjugate base, and the first instance here means if I go backwards, I am dealing with an acid. So in this case, it would be acting as an acid. Definition of an acid is something that will donate an H plus, which means I should take off the H plus in this case, and I should end up with CO3. Again, I lose a plus, which means I become one more negative. So this becomes CO3 2 minus in this case. Yeah. Any questions on that one there? Now, if the HCO3 minus, I'm looking for the conjugate acid, much like the original problem. If I'm looking for the conjugate acid, that means in this particular case, it is going to be acting as a base, which means it will actually accept an H plus. So we're going to put the H plus on. When we put the H plus on, we end up with 2 hydrogens, a carbon, an oxygen, and 3 oxygens there. The +1 and the -1 here obviously cancel out to 0, so it has no charge, and we get carbonic acid in this particular case. Any questions first off on the answers there? Now, clearly in this case, this guy could act as an acid or base, and there are certain substances that have the ability to act as an acid or a base. And those guys are what are known as being amphoteric. So an amphoteric substance is a substance that can either act as an acid or a base. And typically speaking, if you run across some guy like this, which has like a hydrogen and a lot of times a negative charge, they do have the ability to really go both ways. They could act as an acid in certain situations. They could act as a base in other situations. Water actually is another example, as we will see, that is something that actually could go both ways. It could act as an acid or a base. And those things are, again, what are referred to as amphoteric substances. Any questions on that there? Speaking of which, that's what we were just talking about, and that is the autoionization of water, for example. Water can act as an acid or a base. It can even react with itself, and one water would act as the acid, the other would act as the base, and that gives us H3O plus and OH minus. So this is constantly sort of occurring in water. You get this reaction between water and other things. And again, it could act as an acid or base. It's an amphoteric substance. Any questions on that there? Okay, I think we're actually gonna lay it up here. It's a good stopping place, I think, before we get into too much of some other stuff.